Let's look at sample problem 5.12 from your textbook, predicting the products of hydration. On this slide are 3 different alkenes, and you're asked to predict the product of hydration. We're adding water in the presence of acid. So pause the video and see if you can determine the product of the hydration of these alkenes. So we're going to apply Markovnikov's rule, and we look at this double bond. We want to see if each carbon is symmetric on each side, and they're not. This has 1, 2, 3, 4 carbon atoms. The double bond is actually between the 1 and the 2 carbon. I numbered it the wrong way. And in this number 1 carbon, there are 2 hydrogen atoms, and in the 2 carbon, that only has 1 hydrogen, and it's also bonded to an ethyl group. So the 2 carbon is going to preferentially receive that hydroxyl group for the alcohol. So if we look at the main product, it's going to have 1, 2, 3, 4 carbons, and the hydroxyl group is going to be bonded to that second carbon. If we look at the next alkene, it's drawn as a skeletal structure. So it's useful to translate the skeletal structure to a Lewis structure. So here we have carbon double bond here, and this carbon is bonded to 2 methyl groups, and this carbon is bonded to 1 methyl group and 1 hydrogen. So we see that this carbon, which would be the 1, 2, 3, 4, I'm not going to take the time to figure out the numbering, but this carbon that is bonded to 2 methyl groups is the carbon that is going to preferentially bond to the hydroxyl group from the water. So if we look at the solution, it's in a skeletal form, and I drew my skeletal form a little bit different. This carbon is the carbon that's going to have the hydroxyl group, and this carbon will just get a hydrogen. So when we go from the skeletal structure of the alkene to the skeletal structure of this alcohol, this is what we get. This carbon right here has 2 methyl groups. That has the hydroxyl. And the other carbon that only had 1 methyl group gets the hydrogen. All right, now let's look at our last alkene that had a double bond here. This is cyclohexene, and it really doesn't matter. Both of these carbons are symmetric. If we look at this carbon on the double bond, 1, 2, 3, 4, and then this carbon on the double bond, 1, 2, 3, 4, before we get to the double bond again. So regardless of where we put that hydroxyl group, it doesn't matter. It would still be called the 1 position. So our cyclohexene has a double bond where the carbons are symmetric. They're exactly the same. And there is a plane of symmetry. If we are to draw a line right here, both sides of that line would be exactly the same.